This is part 5 of the series Congruent Triangles. We're going to start this session with some examples on using the three triangle congruence postulates: side, 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 side angle, side, and angle, side, angle. In this example, we have a quadrilateral that gives us that BC is parallel to AD and BC is congruent to AD. So this is the congruent symbol. This is the parallel symbol. So what postulates can we use, or if any, to determine if these two triangles are congruent? Well, given the fact that this is parallel to this, then we know that we have two parallel lines cut by a transversal. That makes this angle congruent to this angle because they're alternate interior angles. If two parallel lines are cut by a transversal, then the alternate interior angles are congruent. We also know that AC is congruent to itself by the reflexive property. So we would write AC is congruent to AC by the reflexive property. Property of segment congruence. Now, since this is congruent to itself, we have side, angle, side, side, angle, side. Always remember that you have to take the short distance between the elements. You can't say, for example, side, skip this angle, go to side, and then the angle. Can't do that. You've got to take the shortest route. Side, angle, side. Not to mention that that wasn't a theorem. So that's all we have at this particular point is side, angle, side, angle, and side, side, side. So these two triangles can be shown congruent by side, angle, side. Let's try another example. In this example, we have triangle WXZ and triangle YXZ. We see that WX is congruent to XY, WZ to ZY. Now what we should see, at this point you should be recognizing when you have things joined together that this segment is shared by both triangles, so therefore XZ is congruent to itself by the reflexive property. And so because XZ is congruent to itself, we have side, 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 side. So these two triangles can be shown to be congruent by the side, side, side postulate. Now in this example, we have two triangles that have two parallel sides. Whenever you see parallel sides, you should always be looking for alternate interior, alternate exterior, any of those angle pairs from previous units. So in this case, I know that since these are parallel, I know that this has to be congruent to this because they're alternate interior angles. And the other thing that jumps out at me is that I see these two angles are a vertical angle pair. So I know then by the vertical angle congruence theorem that this angle is congruent to this angle. So here I have angle, side, angle, angle, side, angle. So I can show these two triangles are congruent by angle, side, angle. Now this was just a small set of the types of problems you'll encounter related to these three postulates, but I hope it'll serve as a guide to help you solve those problems. So let's go ahead and move on to the next section. Now in addition to our three postulates for triangle congruence, we have two theorems. The first theorem we're going to look at is the angle-angle-side congruence theorem. What it says, if two angles and a non-included side of one triangle are congruent to two angles and non-included side of a second, then the triangles are congruent. So here we have the two angles, and here we have the non-included side. So this side is not between the two congruent angles, so that's a non-included side. Now this theorem might not be intuitively obvious as to why it works, but the proof is fairly straightforward. So let's go ahead and work that out so we can see where the angle-angle side theorem comes from. So I've gone ahead and pulled up our proof grid, and I put in our given statement that angle A is congruent to angle D, angle B to angle E, and AC is congruent to DF. What we have to prove is that these two triangles are congruent. So the first thing I see here is that because I have two angles of one triangle congruent to two angles of a second triangle, these two angles have to be congruent. That's the third angle theorem. And given that those two angles are congruent, what I can do is then use the angle-side-angle postulate to show that these two triangles are congruent. So as it turns out, this proof's not going to be so terrible after all. So we can say that angle C is congruent to angle F, and that is the third angles theorem. And then we know, since we know this is congruent to this, then we can say triangle A, B, C is congruent to triangle D, E, F by angle, side, angle. Congruence postulate. So now that we've proven the angle-angle side theorem, it's now available for us to use to prove triangles congruent. So let's go ahead and look at an example. In this example, we have a quadrilateral PQRS. We have two right angles here, and we're given that PQ is parallel to RS. Again, parallel lines, we should be looking for transversals, an alternate interior, alternate exterior, any of those things. So as we look at this, we can see that since these are parallel, this angle and this angle are congruent because they're alternate interior. Now, we also know that because this side is shared by both of these triangles, that this side is congruent to itself by the reflexive property. And so here we have an example of angle, angle, side. Angle, angle, side. Again, we can't go side, skip this angle, skip this side, angle, angle. All right? It doesn't work quite that way. So you've got to take the shortest path. Angle, angle, side. So that wraps up that example. Now before we look at the second theorem of triangle congruence, hypotenuse leg, we're going to need to take a little bit of a detour, and we're going to do some investigation of isosceles triangles first. And then we'll come back to the hypotenuse leg theorem at a later time. So let's go ahead and start in on our investigation of isosceles triangles. We were briefly introduced to isosceles triangles back at the beginning of this series when we looked at classifying triangles by their sides, and we learned that isosceles triangles are triangles with exactly two congruent sides. But what we're going to do now is we're going to look at the parts of an isosceles triangle first and do a little deeper analysis of what makes these things tick. So first, we're going to look at the congruent sides. These congruent sides are called legs. So the legs of an isosceles triangle are the two congruent sides of the triangle. The legs are adjacent to a side called the base. So the base is the side adjacent to both legs. So this is the base of an isosceles triangle. The two angles that we have, that are adjacent to the base are called base angles. So it's the angles adjacent to the base. The sides of the base angles are a leg and the base of the isosceles triangle. And lastly, we have something called the vertex angle. The vertex angle is the angle opposite the base. So this angle is opposite the base. You go straight across and there's the base. Straight across, there's the vertex angle. And the sides of the vertex angle are the legs. So you could say that the vertex angle is the angle made by the legs of the isosceles triangle. So that's the basic anatomy of an isosceles triangle. Now we want to look at what happens in relation to these legs and these base angles. The theorem that relates the legs of an isosceles triangle and the base angles is called the base angles theorem. And it says if two sides of a triangle are congruent, then the angles opposite those sides are congruent. So since AB is congruent to BC, then angle A must be congruent to angle C. So let's do a proof of this theorem to see how this thing actually works. So here I pulled up our proof table and I've written in the given information. Now what I'm going to do to be able to prove this is I'm going to have to add some information with an auxiliary line. I'm going to draw a segment from the vertex to the midpoint of AC. And we're going to call that point D. So now with this auxiliary line, let's get started in writing our proof down. So the first thing I did is draw BD, D is the midpoint of AC. And the reason for that is the 2-point postulate. So 2-point postulate, which says through any 2 points there's exactly one line. Now because of the addition of that auxiliary line, I know now that AD is congruent to DC. So AD is congruent to DC. These are segments. And that is definition of a midpoint. And I can put in some marks here. And I also know that BD is congruent to itself by the reflexive property. So BD is congruent to BD. And that's reflexive property of segment congruence. And now, since this is congruent to itself, I know that these two triangles are congruent by side, side, side. So I can say triangle A, B, D is congruent to triangle C, B, D. Side, side, side congruence. And therefore, I know that angle A is congruent to angle C. Because of the definition of congruent triangles, that the corresponding parts of congruent triangles are congruent. So I know that this angle is congruent to this because of corresponding parts of congruent triangles are congruent, and we abbreviate that C, P, C, T, C. Corresponding parts of congruent triangles are congruent. And that gives us the base angles theorem. So we know that if two sides of a triangle are congruent, the angles opposite must be congruent. So now let's move on to the next section.